Off Japan's coast, the Pacific creates one of engineering's harshest construction environments. Yet across these dangerous waters, engineers imagine a permanent highway connection.
Today, we explore how Japan could build this breathtaking $40 billion ocean bridge.
Its most remarkable feature is a hollow marine tower containing a spiral highway.
Subscribe as we follow every stage, from seabed survey to final operation. The proposed route spans waters too wide for conventional short-span bridge construction.
Below the surface, the seabed drops sharply through weak and uneven sediment layers.
The route also lies near active faults within the Pacific Ring of Fire.
Typhoon waves can produce enormous horizontal forces against exposed marine foundations.
The central question is simple. How can any structure survive here permanently?
Existing coastal routes are congested, indirect, and vulnerable to natural disasters.
Delays between ports and factories increase transportation costs across the national supply chain. A direct ocean crossing could remove hours from critical freight journeys.
Emergency response also depends on transportation corridors available during regional crises.
Millions of residents and major industrial zones could benefit from improved connectivity.
The bridge must support continuous freight movement between ports, factories, and inland markets.
Forecasts indicate existing routes will eventually exceed their practical traffic capacity. A separate ocean corridor could provide essential redundancy after a major earthquake.
The design must carry highway traffic without obstructing international shipping lanes.
Achieving those goals requires a structure unlike any ordinary sea bridge.
The project begins with a detailed investigation of the proposed marine corridor. Multibeam sonar sends thousands of acoustic pulses toward the seabed below.
Returning signals reveal underwater slopes, trenches, ridges, and possible foundation locations.
An autonomous vehicle examines areas too deep and dangerous for divers.
Close inspection confirms seabed conditions change dramatically across short distances.
Geotechnical crews drill core samples deep beneath the proposed central foundation.
Each sample preserves the strength and composition of the underground layers.
Laboratory tests measure how soil behaves under pressure and repeated movement. Ocean bottom instruments record small tremors and map active fault movement.
Weather buoys collect an entire year of waves, currents, and wind data.
Historical storm records establish the maximum environmental forces used for design. The survey exposes the greatest threat: unstable sediments above an active seismic zone. Standard bridge foundations would depend heavily on soil lacking reliable support. A slender pier would experience extreme bending under repeated typhoon impacts. Sudden ground movement could transfer destructive earthquake forces into the structure.
Engineers compare caissons, artificial islands, floating systems, and deep pile foundations.
A conventional artificial island would consume excessive material and disturb surrounding currents. A floating bridge would struggle during typhoons and major seismic events. An unsupported navigation span would create structural lengths too difficult to control. The central tower must distribute traffic without creating dangerous roadway gradients.
Thick marine concrete can overheat internally and crack while curing.
Microscopic cracks could allow chloride penetration and accelerate reinforcement corrosion. Heavy segments require millimeter alignment while moving above rough water.
The solution must resist waves, earthquakes, corrosion, settlement, wind, and ship impact.
The selected concept begins with a massive hollow cylindrical central foundation. Its components distribute vertical, lateral, and seismic forces throughout the structure. Large steel piles bypass weak sediments and anchor into stronger geology. Concentric pile groups distribute loads evenly beneath the enormous marine tower. Curved wall sections create a rigid shell resisting multi-directional wave forces. Inside, a spiral highway manages elevation while maintaining safe driving gradients. Continuous box girders transfer bridge loads smoothly into the central support.
Sulfate-resistant, high-strength concrete protects foundations from aggressive seawater exposure.
High-strength tendons compress each segment and prevent excessive tensile cracking. Multi-directional bearings isolate deck movement during earthquakes and thermal expansion. A protective ring reduces wave energy and shields against vessel collisions. Together, these systems transform separate challenges into one integrated structural solution. Construction begins by creating a controlled safety zone around the offshore site.
Temporary routes separate commercial traffic safely from heavy construction vessels.
Dredgers remove unstable surface sediments and expose consistent bearing layers.
Sonar checks confirm excavation reaches the required profile and elevation.
Precisely graded rock creates a level base for foundation installation equipment.
A floating concrete plant reduces travel time during continuous offshore pours.
A dedicated service dock organizes the daily flow of workers and materials.
A specialized onshore yard will manufacture thousands of precision structural components.
Heavy lifting systems arrive in modules for assembly near the corridor.
Safety crews rehearse storm evacuation, medical response, and marine rescue procedures.
Real-time monitoring provides early warning of dangerous weather and geological movement. With access, monitoring, and logistics established, component production can begin. Production starts by shaping high-strength reinforcement for concrete bridge segments. Each cage follows precise geometry for bending, shear, and torsional loads. Controlled welding preserves dimensional accuracy without weakening critical steel components. Embedded systems are positioned before concrete encloses the internal structure. Precision molds create matching surfaces for accurate segment connections. Temperature-controlled ingredients limit heat generation inside massive concrete sections.
Describe as controlled concrete forms the bridge's strongest structural components.
Vibration removes trapped air and ensures contact around dense reinforcement.
Internal cooling prevents dangerous thermal gradients during early curing.
Controlled steam curing develops strength without drying or cracking concrete.
Ultrasonic inspection searches for voids, cracks, and incomplete consolidation.
Fiber optic instruments verify every tendon reaches its specified pre-stressing force.
Proved modules use custom cradles, preventing distortion during transportation.
Heavy barges deliver components along a carefully monitored marine corridor. Foundation construction begins by positioning the first deep steel tubular pile. A hydraulic hammer advances the pile toward stronger geological material below. Underwater cameras verify vertical alignment while the pile enters the seabed. Driving resistance confirms each pile reaches the intended load-bearing layer. Dozens of piles gradually create the circular skeleton beneath the tower. Internal reinforcement strengthens the pile head before concrete filling begins. Tremie placement prevents seawater contamination during underwater concrete filling. A circular cofferdam isolates the central foundation from the surrounding ocean. Powerful pumps create a controlled dry chamber above the foundation area. Radial reinforcement ties every pile into one continuous structural foundation. The base slab is poured continuously to avoid weak construction joints.
Embedded sensors guide cooling as heat develops inside the concrete mass. Heavy cranes assemble the first ring of the cylindrical outer wall.
Laser systems position adjoining modules within millimeters before permanent connection. Circumferential tendons compress wall modules into a unified structural shell. Climbing formwork raises the tower, while internal floors stabilize its height. The inner core supports road decks, utilities, elevators, and emergency systems. Radial columns create supports for the internal spiral highway. Prefabricated deck sections form a continuous roadway with controlled gradient. Above the sea, a launching gantry assembles the long approach bridge. Each segment rises into a precisely controlled installation position. Epoxy joints and post-tensioning lock the bridge into continuous compression. Offshore sensors suddenly detect rapid movement along a nearby seismic fault. Seismic waves arrive before the unfinished structure achieves full rigidity. Precision instruments record unexpected lateral displacement across the upper tower.
Several curing sections develop small cracks as the foundation shifts.
The earthquake is followed by a powerful typhoon moving offshore.
All lifting stops before rising winds destabilize suspended equipment. Crews lock machinery and reinforce every exposed temporary connection. Non-essential personnel evacuate while specialists secure critical monitoring systems.
The final site team leaves before helicopter operations become unsafe.
The unfinished tower faces earthquake damage and an approaching super typhoon.
Embedded sensors report the structure's condition throughout the typhoon. Measured movement is compared against predicted limits for critical structural zones.
A combined model reconstructs how earthquake movement initiated the cracking.
Temporary restraints concentrated movement into several curing concrete sections. Underwater vehicles confirm the primary piles remain stable and undamaged.
Three-dimensional laser scanning measures alignment changes across the entire tower.
External tendons restore compression and redistribute forces around the shell. High-strength grout seals repairable cracks and restores environmental protection. Expanded wave barriers reduce future impact forces against vulnerable sections. Verification confirms the reinforced structure satisfies every required safety threshold. Construction shifts from structural work to integrated operational systems. Independent backup power maintains lighting, pumping, and emergency communications. Powerful pumps remove seawater intrusion and storm runoff from the tower. Ventilation controls exhaust, heat, humidity, and emergency smoke movement.
Adaptive lighting guides drivers through changing elevations and enclosed roadway sections.
Permanent sensors measure strain, vibration, temperature, settlement, and corrosion.
The central control room tracks every vehicle entering the offshore structure.
Automated signs regulate speed and close lanes during dangerous weather.
Protected escape routes guide drivers toward secure areas during incidents.
The rooftop landing zone provides direct emergency medical access.
Final testing begins with complete inspection of every structural connection.
Loaded test trucks apply known forces across selected bridge spans.
Static loading confirms measured deflection matches the engineering prediction. Dynamic testing measures vibration from moving vehicles and changing load positions.
Bearing tests reproduce earthquake displacement without damaging the completed bridge.
Drainage trials verify pumps prevent dangerous water accumulation inside the tower. Traffic systems respond automatically when wind exceeds safe operating limits.
A coordinated drill tests operators, rescuers, police, and medical teams.
All structural, electrical, drainage, traffic, and emergency systems pass verification.
Subscribe as the first official vehicles enter the completed ocean corridor.
The new route shortens journeys between ports, factories, and coastal cities.
Inside the tower, the spiral highway distributes traffic across multiple elevations.
International shipping continues through the protected navigation channel below.
The corridor strengthens emergency mobility and national transportation resilience.
What once divided these shores now stands as a monument to disciplined engineering.